Okay, topic I'm about to teach, limiting reagents. Probably in stoichiometry the hardest topic to teach. So let me try to give you an analogy to help you understand it first. So limiting reagent, what it means by definition is, so when we do a reaction, right, you are going to have one of the reactants is going to run out first. And what happens is, when that reactant runs out, the reaction stops occurring, right? It's kind of like fireworks, you know. The reason they don't keep going and going and going is eventually you run out of the reagent. Well, I'm going to paint you a picture, okay? So we're going to build bikes. So if in order to build a bike, we're just going to say you need one frame, 1F, plus 2W for wheels. So one frame and 2 wheels makes 1 FW2. Me, I take the things and I put them together to make one bike, right? So one frame plus 2 wheels equals one whole bike. Now I know there's a chain and reflectors and all that good stuff. But for our purposes, we're going to say that, okay? So here's like an analogy of what a limiting reagent would be. So let's say I gave you 10 frames, and I gave you 10 wheels. And I was to ask you, how many bikes could you make from these components? 10 frames, 10 wheels. Well, we know that it's going to take one frame, so you should be able to make 10 bikes, right? But it's 2 wheels in a bike. Well, if you only have 10 wheels, you end up with 5 bikes. So what ends up happening is the limiting reagent is the wheels, because you're going to run out of these 10 wheels at 5 bikes, right? And you're still going to have 5 frames left over. We call that something called the excess, or to be even more confusing, sometimes you'll see this as the non-limiting reagent. I don't like it when they call it that. I prefer they call it the excess. But the limiting reagent is the one that's going to run out first, because you'll be out of that when you make 5 bikes, right? So the best way I think to teach this is to go through an example problem, and it's going to be an extensive problem. So pay attention in your packets. I am on page 8 in your packet, page 8, and I'm going to do the first problem 1 through 5 with you. So number 1, so we're on page 8. We're going to do 1 through 5. It's going to be extensive. So it says, number 1, write the balanced chemical equation for the reaction above. And it's when copper 2 chloride reacts with sodium nitrate, copper 2 nitrate and sodium chloride are formed. So that comma is important. So it says when copper 2 chloride, so for number 1, Cu, Cl is minus 1, therefore it is CuCl2 plus sodium nitrate is NaNO3 plus 1 minus 1 reacts to give copper, still version 2, nitrate, which is NO3, and the reason I'm saying I need 2 of them is because -1, and NaCl, right? Plus 1 minus 1. Now, what we do need to do is we get rid of our charges. I always make sure I do that little part. It's important. It just makes it look cleaner and easier. And now we have to balance this chemical equation, right? So I found myself saying, okay, what do I got to balance here? Well, I started with 2 chlorines and 1 chlorine there. So I said, you know what, let's try a 2 right there. That gives me 2 chlorines, but it also gives me 2 NAs. Well, if I put a 2 right there, that gives me 2 NAs. 2 NO3s, 2 NO3s, balanced chemical equation. So there's number 1, having a balanced chemical equation. Again, I'm going to get rid of this stuff. Why? Just because it's in the way. I don't want it there. All right. So here we go. Number 2. It says if 15 grams of copper 2 chloride reacts with 20 grams of sodium nitrate. So you're told that you have 15.00 grams of this and 20.00 grams of this. It says, how many grams of sodium chloride can I make? So question, grams over here. Okay? So question number 2. So what you got to figure out, guys, is this. Is the 15 grams of this or the 20 grams of this going to run out first? Which one's going to be out? Well, here we go. What you do is you take what you start with, which is 15.00 grams of CuCl2, and you turn it into moles. Now, to go from mass to moles on the flux capacitor is dividing by the molar mass of the substance, which would be CuCl2. The molar mass of CuCl2 is 134.45 grams. Okay? You do the math on that and you get 0.1116 moles. Now, I usually don't care too much about significant figures here. What I do is I give myself like 4 digits or 5 digits, whatever. Okay? I'll care about significant figures later. Now that tells me how many moles I have of CuCl2. Then likewise, you had 20 grams of NaNO3, right? Well, grams into moles divide by the molar mass. So the molar mass of NaNO3, 22.99, 14.01, and 3 times 16, right? And that is 85. So that ends up being 85 grams. You divide this out and you get 0.2353. Now, there is one thing you cannot forget to do, and it is super important. Remember on the last example I said, okay, we had 2 wheels for every 1 frame. Well, here you have 2 NAs for every 1 CuCl2. So you got to account for that right here. This one, there was only 1, so you divide it by a 1, it would be the same. But you're going to go through 2 of these for every 1 of those. So you have to take this number and divide it by the 2 right here. So you divide this by 2. And you get a number, and that number is 0.1176 moles. Now here's the question. 0.116, 0.1176, which one is smaller? Well, 0.111, 0.117. Therefore, the smaller one is this one right here, the CuCl2. Therefore, making it the limiting reagent. Okay? Now, we're still not done with this problem because now here's the hardest part. We know that this 15 grams is going to run out of CuCl2 is going to run out before this 20 does. So what we do is we start with that. And now we're going to do some dimensional analysis. This is going to get interesting. So grams of CuCl2, and we're going to do a big dimensional analysis. First thing we do, we take grams of CuCl2 and we turn it into moles again. Now I like doing dimensional analysis because here's why. In 1 mole of CuCl2, there is how many grams of CuCl2? Well, it's called the molar mass. We already calculated up here, and it's 134.45. Which brings us to the most important step. It's called the mole ratio. And it is the key to limiting reagents, mole ratio. Well, we got rid of grams of CuCl2, right? And we're left with moles of CuCl2. But this question wants to know how much NaCl we're going to make, right? So here is how you do it. Mole ratios allow us to compare moles of one thing to moles of another thing, okay? Well, here on the top you have moles of CuCl2, so I'm going to put it on the bottom here. Why? So that it cancels. Now, we go find the balanced chemical equation, put a number right here. We go find CuCl2, there is a 1. So for every 1 mole of CuCl2, we want to know NaCl. So on the top of the mole ratio will always be what you are looking for. Let me say that again. On the top of your mole ratio step, the thing that you're looking for will always be on the top. Well, the number here is we're going to go through 2 moles for every 1 of these. So therefore we put a 2 right there. Now, if I was asking you how many moles of NaCl, you could stop right now. But that's not what I'm doing. I'm asking you how many grams there are. So you have one more step, and it is this. in 1 mole of NaCl, we can calculate how many grams of NaCl there are. It's called its molar mass. So when you take 22.99, 35.45 and put them together, you get 58.44 grams. Well, moles gets rid of moles, leaving you grams of NaCl, grams of NaCl. Now, we started with 4 significant figures right here. Always what you start with, 4 significant figures. And I'll try to make these numbers match if I can. But we have 4 significant figures, therefore our answer can have 4 significant figures. So when we do the math on this, we get 13.04 grams NaCl. And believe it or not, guys, in order to give the answer for question number 2, you had to do all this work. So let's review real quick. What we did, we took the grams of each substance. We divided by the molar mass to get moles, right? Because that's the flux capacitor. We did here, divided by the molar mass. We had moles and moles. We said, okay, we're going to go through 2 of these for every 1 of these. So we divided this by a 1. We don't need to do anything. And with this, there's 2 of them, so we divided by a 2. We looked at these 2 numbers. We said to ourselves, this one is smaller than this one. Therefore, the smaller one runs out first, just like the wheels on the bike's analogy. So that makes this the limiting reagent. The thing that's going to run out first, you always start with the limiting reagent. We took the limiting reagent, we turned it into moles. This is called the molar mass right here. That's the moles, or grams in 1 mole of it. Most important step, mole ratio. We knew moles of CuCl2, so they go on the bottom, and we get that number 1 from right there. Then, moles of NaCl, why on the top? Because that's what we want to know. If we wanted to know CuNO3 too, it would have been that on the top. But in this case, we want to know NaCl. There's a 2 here, so that's why a 2 is there. The last thing is I wanted grams of NaCl, not moles of NaCl. If I wanted that, I would have stopped right here. It would have been moles of NaCl, put an equal sign, do the math. But I need to do one more step. In 1 mole of NaCl, there's 58.44 grams. Therefore, you do the math, right? Now, with fractions, you multiply the tops across, divided by the bottoms all the way across. Now, if you need a placeholder here, you can put a 1, right? Then you would divide it out. 4 significant figures in 15.00, 4 significant figures in 13.04 grams NaCl, and that's the answer for number 2.